I would like to welcome you to the first Detroit Tech Watch and Collider partnership of 2022. My name is Ryan Nico, and I am here representing Collider, which is a community hub for tech professionals who are leveling up their skills with digital business innovation. And as usual, we're proud supporters of the Detroit Tech Watch, and we are here to help you level up your tech career. So I will drop a link in the chat, and then you can check us out later when you have some time. Also, I will drop my email in the chat. So if you have any specific questions, do not hesitate to reach out. But Onario or Mike, please take it away.
You want to take it, Mike, or you want me to?
Why don't you go for it? Because you have a little bit more. You invited Marcus. Also, I'll just quickly say, Marcus, welcome. Thanks for joining us today. I'm excited about this.
Thanks for having me.
Okay, so without belaboring the point too much, I saw Marcus down at Strange Loop last year, and TLA Plus is something I've been very interested in for a couple of years now. And Marcus gave a great session, like a day-long tutorial on it, and I thought maybe I can get him just to give us a brief intro. It's really a really neat tool, and I don't want to steal any of his thunder, so I won't say anything more. But without any further ado, Marcus, take it away.
Okay, sure. Yeah, well, hi, everybody. I happen to be an engineer working at Microsoft on TLA Plus for about a decade now, just to give you a rough idea on my level of expertise, I would say. I work on the tools, but I also train engineers at Microsoft in TLA Plus and generally just try to make it usable and help more teams adopt it. In terms of today, what I want to show you is kind of like an excerpt of what Onario mentioned. First of all, I will give you the executive level summary introduction to TLA Plus with a handful of slides. This is where you can lean back and just listen. But then once we get to number 2 here and 3 and 4, I need your help because I want to use TLA Plus to really debug a deadlock in an existing system. And we will see kind of 2 cornerstones or core features of TLA Plus. Formalization of safety and liveness, deadlock, starvation. And then since this question pops up pretty much always, I want to share a little bit of how to connect your implementations to TLA Plus specifications before I give you the homework assignment to really design something novel with TLA Plus, namely the termination for this multi-producer, multi-consumer queue. But let's get started first. Okay, so the 30,000 feet above perspective on TLA Plus is, if you go to Wikipedia, it's a specification language to design, document, and verify reactive systems. So let's unpack this from the back. So reactive systems are concurrent systems and distributed systems usually. So those that exhibit a lot of non-determinism and are thus pretty hard, at least compared to sequential algorithms. Sequential algorithms already are difficult, but reactive systems are even more difficult. So here we need a strong tool support to get them right. But what's more important is initially that TLA Plus is the specification language. So it's not a programming language, and its goal is so that you design your system before it gets implemented and you document it. And that way, don't create a couple of bugs that you then would later implement, right? So it prevents you from implementing bugs. Its creator, it's this person here, and this is not Photoshop. This is taken from his recording, his tutorial introduction to TLA Plus. He's better recognized by this picture here. He's Leslie Lamport, Turing Award winner of 2013. So he made several contributions to computer science in the area of reactive systems. And you can kind of see TLA Plus as the tool that he wished he would had at the beginning of his career when he worked on Paxos and the bakery algorithms and all those difficult reactive systems. And what he really wants to stress now, what I have to stress is that TLA Plus, once again, is not programming. The idea here is that create a new artifact in the software development process that's in between our prose documentation and our implementation. Just recently, I was presented a prose document, about 60 lines or so of Word in a Word doc. I translated it into 600 lines of TLA Plus, approximately. I think once this gets implemented, it's perhaps 6,000, 60,000, 600,000 lines of code. Now, without TLA Plus, there's this huge disconnect between the prose and the actual implementation. If we really want to understand something, the prose document doesn't have enough semantics, and the implementation, it's just too much detail. And TLA Plus tries to be kind of the middle ground here. And this is the fundamental idea. We have a new artifact, another truth in the software development lifecycle. And also, we don't sell snake oil here. It doesn't free you from thinking, right? It's not a tool where you insert your program code and then you get a yes and no answer out that says correct, incorrect. Quite to the contrary, it's actually just a thinking aid that helps you to be more powerful and to catch your thinking mistakes. But it doesn't free you from thinking. Okay. The perhaps most prominent application of TLA Plus was written about in 2013, 2014, when a group of Amazon AWS engineers designed systems such as DynamoDB or S3, and I don't know, a few others. And for those that don't know, DynamoDB is this planetary scale NoSQL database. So replication, there's a lot of stuff that can go wrong, right, when you operate this system. So you have to account for all of these failure cases. And the initial design they wrote, they used whiteboard designs, design discussions, handwritten proofs to convince themselves, okay, this can work. And then they wrote a prototype, right? This is what the usual software development process looks like. Sketch a design, implement it, test the hell out of it, and then rinse and repeat. And then later in production, learn that you didn't catch all the corner cases. So they were kind of probably smart and looked at various formal methods. They happened to like TLA Plus best, and they wrote a TLA Plus specification for DynamoDB. And this logic checker TLC, this tool that comes with TLA Plus, even after this design was prototyped and tested, still found a bug. And this bug manifested after 35 steps. In an implementation, it probably translates into way more steps, but at a high level spec, level, it will those were 35 steps. I think humans usually can handle like 7 to 9 variables, right? So 35 steps is pretty difficult to reason through without getting lost. They were pretty happy with it. Long story short, they wrote in the CACM paper here, using TLA Plus in place of traditional software, proofwriting would thus likely have improved time to market, in addition to achieving greater confidence in the system's correctness. And if you want, you can read the paper, and there's plenty of detail in there. But it got strong support and adoption inside of Amazon, which is funny because TLA Plus is a Microsoft research project. So we're kind of competitors, if you think that way. Okay, so this is obviously way too big to look into within 1 hour or so. So I have a slightly simpler problem. Let's just pretend our production had an outage a couple of days ago. Something went wrong. Somebody came in to save the day by turning it off and on again, right? But now we're kind of tasked to do the post-mortem. And by looking at log files and sifting through all the information we can get, we found that there is a deadlock. And a deadlock in a multi-producer, multi-consumer queue. So we have a set of producers. Here in this picture, we have 4. We have 3 consumers. The producers add element into this buffer, which happens to be 3 elements large. But for some reason, the buffer was full, yet all threads were blocked. All right, this shouldn't happen. Classical deadlock. How can that be? Okay, and now comes the part where I need your help to figure out what went wrong. So here is kind of the C code that we found in our system. We initialized the buffer, okay? It's statically initialized to a fixed size. It doesn't grow, it doesn't shrink, it just gets initialized to so and so many elements. In the picture, it was 3. Then we have like 4 producers, so we spawn 4 producer threads. And we have 3 consumer threads, so we spawn 3 consumer threads. And they execute the producer and the consumer function, okay? So let's move up there. So producer, straightforward. There's a while loop and non-terminating while loop. We acquire a mutex, so log, we get hold of the log, the producer who's currently executing. If the producer finds that the buffer is full, okay, that can happen, right? It waits. And this is the only thing it can do, right? It waits on this modify condition. And it keeps waiting until the point that somebody else sends a signal. So the producer resumes again. It finds that the buffer is no longer full. It adds an element to the buffer. It in turn signals somebody else, and it unlocks the mutex. And the consumer kind of does the inverse, except that it checks the buffer to if it's empty or not, right? If it's empty, it waits again. Otherwise, it removes the head element, it signals, and it unlocks. And we don't even care where this element goes that it removes from the buffer because we're just interested in the deadlock. Okay, so in other words, there's no real interleaving here, right? So whenever somebody is a producer holds the producer, the mutex here, there are no consumers actively executing. And likewise, there are no consumers executing when there is a producer inside of this critical section here, appending an element to the set, to the buffer. Okay, so does anybody care to venture a guess of what the problem is? How can this thing possibly deadlock? Well, I guess we do what we always do when we try to reproduce a bug. We write a test.
I'm sorry,
case, right?
I was trying to unmute my audio.
Okay.
Did I manage?
Yep,
Anybody else cares to unmute their audio and take a stab at it? Let's not leave Marcus hanging.
Yep.
Yep. Or if you're shy, put it in the chat, perhaps. We're paying attention.
Well, I have this test case for you here, so I got you covered. The only thing I need from you is what should I enter here in terms of buffer size, producers, and consumers? Do you want me to get started with, I don't know, a buffer of 124, 512 consumers, 512 producers, or do you rather want me to do one buffer of size 1 producer, 1 consumer? What do you want? Ballpark number here.
I don't know. Let's start with 10, 10, and 10.
10, 10, and 10. Okay. 10, 10, and 10. That's yeah. Okay. Perhaps.
You think maybe larger?
No, it's fine. See, it's running. So now we wait. Okay. Let's see if this deadlocks. And let me just quickly check that I didn't accidentally run the correct version. Nope, it's the broken version. Otherwise, it wouldn't be fair, right? So while this is running and hopefully eventually exhibiting the deadlock, let's move over here and look at the TLA Plus specification. I will make this smaller. So here on the right, we now have our C program, and I will explain to you how this translates into a TLA Plus spec. Okay, it looks a little bit more different. It looks different to program code because TLA Plus is actually logic. So it looks more mathy, less like C or an imperative programming language. But fundamentally, it all describes computations. Might take some getting used to, might even scare you away because perhaps you didn't like math in school, but it's really not that difficult. Don't get scared away. It's easy. I don't hold an advanced degree, yet I managed to understand this stuff. Okay, we get started at the bottom here, translating this back into C. So what happens here in the init and next is that initially we say, okay, the buffer is empty. This is just syntax here that says the buffer is empty. It's an empty sequence. And this wait set variable here also is initially empty. This one is a set, so it doesn't have order, doesn't have duplicates, and this one is a sequence, so it has duplicates and order. And then we say throughout the computation of the system, we pick a thread that's not blocked, meaning it's not part of this wait set here. And if the one that we pick is a producer, well, then it produces something. If it's a consumer, it consumes something. Producer and consumers are just two constants here, producer, consumer, that don't change. Right? It's just a set of elements, of threads. And please interrupt me if you could have questions. Okay, so now let's get to the interesting part. What does put or producer translate to? It translates to put. This is an OR here. So this symbol is an OR. So we have either this or this. If the buffer is not full, well, then append the element to the buffer, notify. If the buffer is full, wait. Straightforward. There's a question, blurry. Is the screen working fine for everybody?
Actually, I'm seeing the blur that they were seeing as well. I was just about to post in there and noticed some other people were posting in there. Yeah.
Make it even larger if that works.
Yeah, I don't even know if it's that. It seems like video quality, because even you are a little pixelated, which makes the code far more pixelated. So it's really hard to read at this moment. Okay. Well, if it doesn't improve, could try to share the screen if that helps. Yeah, that might be helpful, or like like on share something. And I mean, it's not showing us. I'm not seeing any network issue on my end, but I mean, I'm not sure if you're seeing an issue on your end.
Does this
there
make
you go.
things better?
Much clearer.
Oh yeah, there it is. Back to normal.
Much clearer.
Yep,
Thank you.
Perfect again.
Okay,
Yep.
Cool. Then let me continue. Okay, let's quickly recap here what this put does. So it says a producer is allowed to add an element to the buffer if the buffer is not full, and to notify somebody else. And if the buffer is full, it has to wait. Okay, so it's kind of straightforward to what we've seen over here in the C code. And the buffer, the consumer again is if the buffer is empty, it's not empty, this is not equals the empty sequence, then remove an element and notify. And if it's empty, then wait. Okay, it's essentially equivalent to the C program, just formulated as a mathematical formula. And then I said, okay, TLA plus is not a programming language, so we don't have, P thread condition signal and P thread condition mutex, wait, yada, yada, yada. We have to specify this ourselves. And just to give you an idea, let's see, where is it? So this here is the implementation of P thread condition signal. Okay, so about, I don't know, 200 lines of code, plus the broadcast, plus the system level calls, such as where are the p-sync, cd broad, and so on and so on. So this alone, I think, probably warrants a specification by itself. In the high level TLA plus part, we can specify it like this. Right, so we have a wait. Well, wait means we add this thread, the T here, to the wait set. Okay, and notifiers. Well, if there is somebody, if the wait set is not empty, then pick one and remove it from the wait set. Okay, it's essentially just removing and adding an element to a set. Pretty straightforward. Obviously, in implementation, it's way more difficult because you have to think about all these synchronization issues. But here in TLA plus, an action is always atomic. So this here is atomic. This is atomic. There are no interleavings. This is just taken care of for us. Okay. So nice. By the way, this one still hasn't exhibited the deadlock yet. Okay, let's keep it running and see what we can do with this one here. Unless there are questions, please interrupt me if you have questions. PQ out. So I will check this one now with our TLC checker that the Amazon people liked. And it says, okay, I found 4 states. It found 4 states in the case that there are blocking queues here. A buffer of size 1, 1 producer, and 1 consumer. So the minimal possible configuration. Let's look at this state graph. Make this bigger. Okay, I hope you can see it. So we start in this gray state. The buffer is empty, the wait set is empty. We can do a get operation when that on an empty buffer causes the wait set to contain C1, right? So the consumer has to wait if it tries to get something from the empty buffer. From here, the producer can add an element to the buffer, and then I'm removing the C from the wait set. From here, we can go to this state where the producer tries to produce again. This time it fails because the buffer is full. So the producer gets into the wait set, and we go back from here by consuming, by getting an element again, which makes the buffer empty and the wait set empty. And we can just transition along the arcs here in this graph, right? Back and forth. And surprisingly, there is no deadlock. Okay. There is no state.
See a deadlock there, no.
Yeah, there's no deadlock. That's strange. That's interesting. Okay, let's try something else. Let's try a different configuration. Let's try and increase the buffer to 2. Check model with TLC, blah, blah, blah. Takes no time. Opening this is always a little bit painful. So we get 1 extra state, but again, there is no deadlock, right? So there's no state where the wait set contains both threads. So I go to the next configuration, 2 threads, 2 producers, 1 consumer, buffer of size 1. And this one, yeah, it's done. Let me open this again. Woo, it's way bigger. And I have to make it larger for you. And see, now suddenly there is a state where there's where all 3 threads are on the wait set. Okay, so this is nasty, right? So apparently there are configurations where this thing deadlocks, and there are configurations where it doesn't deadlock. So if you just happen to choose the wrong configuration here in your unit test, you can wait forever. And now imagine a situation where you auto scale or something in the cloud, right? And so far for the last half year or so, it for some reason stayed under this threshold where it deadlocks, and then suddenly it goes over the deadlock, over the threshold, right? So that makes it really difficult to spot. Interesting. So let's try and reproduce this here. So I will instrument this code here, this C code with tracing information. And now I think if we run it with 1 to 1, that's the same configuration as in the other one here, it also deadlocks. Whew. Okay, this takes, I think, looks like 8 states or so, 8 steps. Second time 8. Most of the time it's 8 steps, but now it's more. So there's some non-determinism in here. I think I've seen it go up to 20 states or so based on timing. But most of the time we seem to be lucky here and hit the shortest trace. But remember, there are also Heisenberg bugs, right? That disappear once you start using tracing, because maybe it interferes with the synchronization that's going on STD out and STDR. So luckily, this one isn't a Heisenberg. But if we, for example, try the configuration 111, this runs forever. And I guess with 10, 10, 10, I think it should deadlock. But where do you start reading this trace information? Do you start at the beginning? Oh, and then you're probably staring at millions of lines of trace information, or do you just start at the end and try to reason over your way backwards? That's difficult, right?
Yeah.
So here in this one, so far we've only seen a graph. And if I go to buffer 10 producers, 10 consumers, believe me, this graph becomes a spaghetti ball. It doesn't render even because it gets so big. But there's something better. We don't want to look at graphs. Instead, I would just say, okay, we want the specification to not deadlock. And that's the case if the weight set is not equal to the union of the producers and the consumers. Okay, for as long as the weight set is not equivalent to the producers and the consumers, there is no deadlock. If this one is false, then there's a violation, then there is a deadlock. Okay, makes sense? So let's add this here.
Marcus,
Yeah.
cup.
Yep. What's going on?
Cup. You use that /cup.
Oh, cup. Yeah. Okay. So this is a union.
That's union of sets then.
Right. That combines the producers and consumers into one.
Gotcha. Okay. Thank you.
Okay. So this is one set here, and this one is another set. Could have made it more clear and put parentheses here. But really just that combines two sets. Okay, we don't need this graph here anymore. I think, okay. Let's check this once again. Don't need this stuff anymore. And ta-da, here we no longer get success. We now get an error, 21 states. Our invariant no deadlock is violated. And here we see the 9 states it takes to run into the deadlock. So I can rerun this. Okay, same 9 states again. And this is deterministically gives us the same error trace. I could also change the configuration. I won't go to 10, 10, 10, but let me go to, I believe, 3, P3, P4, C2, C3 here. Let's turn this into C and check this. So now some 10,000 states, and the error trace is already 47 states long. So apparently the error trace gets longer the more processes are in the system. That's also strange, right? So if you try and do this with your configuration of 10, 10, 10, I don't know the formula that gives you the length of the error trace, but it would probably be in the thousands or so, if not even longer.
I just got to ask, Marcus, is this a situation where if they're the same, it's 1, 1, 1 or 5, 5, 5 or 10, 10, 10, you won't run into a deadlock, but if they're different, you will, or is it just a coincidence?
I can reveal it later, what the formula is. I mean, what we would probably do here, and the way how I figured it out is I just reran it for a couple of configurations, and then I charted it, plotted it, right? And then I could see it in a 2-dimensional chart where the area where the deadlocks are. So essentially, it's if the buffer is 2 times the buffer size is equal to the cardinality of the union of both sets, producers and consumers, then you have the deadlock. If the buffer is too big, there is no deadlock. There is a deadlock. If the buffer is too small, there is no deadlock. Okay.
Okay.
So it's strange, but let's really drill into this and understand it. In most cases, when you work with TLA+, you will look at this trace. Okay, not at this one, because this one is too long. What you always try to do is to find the shortest possible, the minimal configuration that reproduces the bug. And if you take anything out of today's talk here, it should be that if you test something, start with the minimum first, even with testing. Don't go for 10, 10, 10, go for 1, 1, 1. If that doesn't work, 1, 2, 1 or 2, 1, 1, and gradually increase, and systematically especially increase. So this one has 9 steps. Okay, that seems to be in the area of what a human can reason about. most of the time when you work with TLA Plus, you would look at this, study it, think about it. I said it's a thinking tool, right? So this is what you have to reason through now. Because this is a presentation, can I stop this here? Yeah. Let me just advance my material here. And by the way, you find all this material on the internet, on GitHub. Let's see, I have to go to the animation. Here we are. Because I created an animation with which it's easier to understand the deadlock. Okay, except there is a bug in this PDF viewer, so I have to open it again. Okay, so now we have 9 slides that represent this deadlock here. Just more nicely rendered. So we have our buffer here, it's currently empty. We have our 2 producers, P2, P1, and our consumer over here. P2 is currently active, so it's executing. And in the next state, it's going to add this N element into the buffer. P1 and C1, they are both enabled, so they can run, they're not blocked, but the scheduler hasn't scheduled them yet. So P1 adds the element to the buffer. Okay, the buffer is full. P2 keeps control and tries to add another element to the buffer. Obviously, this fails, right? So P2 gets blocked. Our scheduler, the system scheduler, decides to make P1 the active thread. So it gets control. What it tries to add an element to the buffer. This fails, it also gets blocked. But that's fine, right? Because now it's the time for the consumer to remove the element from the buffer. Okay, it takes the N out of the buffer, immediately again tries to retrieve another element. There is none, so it gets blocked. But since something happened to the buffer, P2 got active again. And now P2 adds an element to the buffer, and it notifies P1. It tries to add an element again, it fails, and now P1 is the only active element, thread. It itself cannot add anything to the buffer, and here's your deadlock. So here, the moment here is where the deadlock actually happens. So it doesn't happen in the last state, it happens in this state because it adds an element, P2 adds an element to the buffer, and it notifies P1, right? And in this case, this is wrong. There are cases where this is fine, right? At the beginning, it's fine to notify P1, right? But in other cases, it subsequently leads to a deadlock. Okay, so what could be the fix?
Somehow would have to make the make adding to the queue atomic.
Well,
I think.
So that's actually atomic. Look at this trace again. So this step is atomic, right? So we atomically add the element to the buffer and send the signal to one of the waiting threads. The problem is with the notification. So if you happen to know the API of pthread condition wait, pthread condition signal, there is a pthread condition broadcast. Okay, so the difference between signal and broadcast is that signal sends a notification to one thread, one waiter, and broadcast sends a signal to all waiters. Okay, so in other words, we do something not like a notify, but a notify all. Let's see if that fixes our specification. So instead, I have the notify all here already because I moved ahead in the Git repository, the Git commits. So this is now the new definition of notify all. Instead of picking an element from the wait set, we now just remove all the elements from the wait set. Okay, this is then equivalent to sending a signal to all of them. So let's see. That seems to fix the deadlock. Nice. So fewer states, that's fine, but the deadlock is gone, right? Now, whenever we signal, whenever something happens with a buffer, we send the signal to all waiters, not just to one waiter, but to all of them. Do you think this is elegant?
So what happens is the consumer starts blocking, and because the consumer is blocked, the producer puts one in there, and then the producer gets blocked, and the next producer is already blocked, so they're all three blocked. So by sending a signal to all three of them, then the consumer says, "Oh, I know there's something there waiting for me. Now I can pull it, so it doesn't block." Am I following you right?
So in this step here, step number 6, when P2, so P1 and C1 are both blocked, now P2 adds an element to the buffer. And previously with notify, it only sends a signal to P1. With notify all, it sends a signal to P1 and C1, and both would become yellow again, or both become yellow again. Okay, and then it doesn't matter if this one, P1 gets scheduled, finds that it's that the buffer is full and becomes blocked again, because it would still have C1 to actually remove the element.
Yeah, so basically you need to notify C1 as well to make sure that C1 knows there's something, or it can check there's something to consume.
Exactly, right.
Okay,
and
that makes sense.
This works, okay? Unsurprisingly, this works. Pretty straightforward reasoning. But now the question is, do you like this solution? So let's imagine we really run this with a buffer of 124, 10,000 producers and 20,000 consumers in the cloud setting or something. And what happens if the buffer is full? Well, then I guess a large number of these threads will block, right? And then what happens if we remove an element? We signal all of them. That's not great. I try to quantify this, what the overhead is of doing this broadcast again instead of the single signal, the notify all compared to the notify. But it seems difficult to really quantify without running elaborate performance tests. But obviously, there's more overhead when you send a signal to n threads, n waiters, compared to just sending a signal to one of them. At least that's what I would expect. I don't know, with modern hardware architectures, sometimes intuition doesn't really work. At any rate, I don't like this solution from the algorithmic perspective, right? Because what is it that we really have to do? Do we really have to send a notify to all waiters? At this point, where should we better send the signal? Should we send it to P1 and C1?
I was thinking
no, just send it to consumers, right?
Yeah, I was just going to say send it to consumers or a set of consumers. Yeah, kind of like a ping pong type thing.
Exactly, right? That would be way more elegant. Instead of using this kind of shotgun approach where you just randomly shoot at a group of things and hope to hit the right one, why not actually be smart about it and really just notify the other type, right? If we notify, if it's a producer that adds an element to the buffer, well, then by thinking this through, you know that the only element that can act on this is a consumer, right? So there's no point really to notify another producer. Well, at least it seems. Maybe it causes another bug, but let's find out. So let's define notify other. There is, by the way, no notify other in P thread condition. There's only broadcast and signal. But here we are free to do whatever we like, right? So I would say this takes some other. And then I say that if the wait set with the other is non-empty, well, then there exists a T in, copy paste this stuff here. And I will, once I'm done typing, I will explain what's going on here, okay? Wait set prime minus T else weight set prime equals weight set. Okay, so here the put notify all gets rewritten to notify consumers. And this one gets written to notify other producers. So when the consumer does a notify other, it notifies producers. So here we get the set of producers. We take the intersection, that's the cap, of the weight set and the producers. So it only leaves the producers in the weight set if there are any, meaning this is non-empty, or then we pick one of them. And in other words, we could say that in this case, it's a type P here, right? And then conversely, notify other for producer, ads, and a consumer. And now we really get, I guess, a typo somewhere. Weight set, right? I think it's up here. This has to be this. And this also works. Okay, for some reason, and this has nothing to do with performance, this has more states. You can kind of think about this way, but if you just individually notify threads, then there are more possible combinations that you can notify threads, right? Compared to when you always notify all of them. So this is why we have more distinct states, but it doesn't mean that it's slower. There's no translation of this into actual performance. But yeah, so this one also works, and I think we all kind of have the intuition that this is at least the more elegant solution. When we have a producer, it notifies a consumer, and if it's a consumer, it notifies a producer. But both solutions fix the deadlock. That's nice. So everybody happy so far? Let's see, where is it? It's this one here. Okay, so we could probably ship this now and send it to production. We would have to figure out how to implement this here, right? Because as I said, there is no notify other. Let me show you how it's done. Well, I guess I can just. Okay, so this should be it. So the trick is, this should have been updated. I guess, I see. So we have to look at the implementation of the same data structure in Java. Okay, it's called array blocking queue in Java, but it's the same algorithm that's implemented in Java, the correct version that's implemented. And the way to implement it is you have a lock. Well, we previously also had a lock, right? The mutex. But instead of just one condition, we have two conditions. We need two conditions. It's like having two weight sets. Okay, we have a condition that says not empty, and we have a condition not full. The producer notifies on one condition, and the consumers wait on this one. And conversely, the consumers notify on the other condition, and the producers wait on that one. So you have this kind of over-cross relationship here between the two conditionals and the producers and the consumers. So and from here, everything else is pretty much the same like in our specification, except there's way more detail here in the implementation of the array blocking queue of Java. Okay, so this would work. Does anybody see problems? Would you now?
I don't know if I understand it well enough to see problems in it, Marcus, but
then ask questions. We're happy to answer questions. So, do you think there's still a deadlock? I mean, we can check it. Just if there's a configuration that you want to have checked, just shoot. If they get too large, it will take too long. But I'm happy to check a different configuration if you want to. But I will.
Well, what if we do it with
1-2-1
1-2-1 again?
1-2-1, sure.
Since that blocked the one time, maybe it's worth trying again.
No, sure. This is it. Check model with TLC. Fine. And I guess I could also show you how to do this for various configurations and then check all of them at once or do this from a bash script, right?
Right.
But no, I promise you that there is no configuration where this deadlocks. This is deadlock free. As a matter of fact, let me do a quick detour here. I have to advance my material a little bit. Okay, so I even have proof that this is deadlock free. Where is it? So TLA Plus not only has a model checker and is a language to describe the system, it also has a proof system and a proof language where here I wrote the proof that the specification is deadlock free. I can run the proof system now on this one, and it will verify that the reasoning is correct for any number of threads and buffer size. So there is machine check proof that this one is deadlock free. It's usually too much work to write this proof. So as most engineers don't spend the time on proving this stuff, but in this particular case, we have proof. Let's see, TLA PM, blocking queue, oh, nope, wrong file. Blocking queue.tla, takes a couple of seconds, but oh, it went through. It doesn't complain about the file, so that means it got proved. So that's not it. In other words, the proof, what it gives us, there are no safety issues with this specification. And yeah, don't try and read this proof here. That takes more time, right? Just wanted to mention that there is a proof system available. But yeah, so this
I think I see what you're getting at, Marcus.
is deadlock free. It satisfies its safety properties. But I guess what could happen if we run this in production long enough that for some reason just some of our customers are unhappy. Okay, most of the time it's fine, but every once in a while one customer doesn't get served, or a subset of the customers don't get served, because it seems it might be that there is some sort of starvation going on here. Okay, so what we really want to make sure is, for example, that for all producers and producers, and now we have to see the temporal part.
Marcus, sorry to stop you, man. You got a typo there.
For all
Producers.
Prod or
producers. Oh yeah, thanks.
No C in there.
You're welcome.
Yeah. Put P, P. There's also vars here. So that should be it. So what this formula now here mandates is that repeatedly, this is what can be read as repeatedly. Again, I don't have time to really introduce the TLA plus syntax here, but you can just read it as repeatedly, every producer executes a put operation. Okay, and adds an element to the buffer. Okay, let's see if that one works. Starvation, and let's add it to the config file. Property starvation, and I believe I have to go back to the config file. Okay, let me just, before I do this manually, there's too much for me to change here. I will just fast forward. Am I fast forwarding? Let's see. Type in, a few more commits. This is a little bit, it's too large to actually see what's going on. Where's the starvation part? Is it done in split? Let me quickly check it here. Nope. Okay, starvation, liveness checking. Okay, here we are. Now there should be, let me make this smaller so I can see more of what's going on here.
You
right.
could
Here it is. Here
click
it is.
on the editor and it'll give you a little more space. It'll take that column way on the left.
Yeah, no, it's fine, I think.
Okay.
So here it is. Here's the line I just typed, okay? Make it bigger again. It was just added below the proof, and I was looking for it above the proof. It should be in the config file. Yep, property starvation. And now let's see if this one checks out. And again, the model checker within very little time shows an error here. That this time, instead of being a sequence that ended in a terminal state, now has this funny state that says back to state. So in other words, we have kind of a loop in here. Well, if you read this through, you will see that there is a thread here, a producer, that never produces an element because it's always waiting and never really adding an element to the queue, which is, I guess, not really surprising because there's nothing in here in our specification that says that this should happen. Okay, and the difference now here between the previous problem we saw, which was a safety violation, this one is a so-called liveness violation. So where a good thing never happens. Okay, and this is one of the features of TLA Plus that you don't usually find in other formalisms, that it has first-class support for both safety and liveness. Most formalisms let you check safety properties, nothing bad ever happens, but they don't let you check the good thing that eventually happens. Here in TLA Plus, this is first class and can happen. Okay, a question about liveness or safety, stuff like that. The way, what's the way here to make this now satisfy its liveness property? What do you think?
Seems like you'd round robin the producers, force it to take turns producing.
Okay, yeah, right. So what would be a good way to make them take turns?
Wish I knew.
So let's see. There's a fair right here. So there's a specification. I've written this specification. It's almost the same specification. Here's your put. Here's your get. Init, next. There are two differences to what we've seen before. First, now there are these two weights, two variables for the waiters, for the consumers and the producers. Okay, that's what I said earlier, right? We need this, two conditions. But now instead of it being a set, this is now a sequence. Okay, so now we have an order. When we add an element, we can have a LIFO, a FIFO order, whatever we want. Obviously, we want to have a LIFO order here. So when we notify a thread, we use the head element, right? And that way we have this guarantee that we get some sort of fairness here. And again, if we would go and look, let's see, maybe I can find it. So this array blocking queue here, when it gets instantiated with the constructor, it has this Boolean here, fair. And this Boolean is actually, capacity, this is the default, that tells the reentrant lock whether or not it should maintain order or not. Okay, there's way more detail again here because this is programming, but this is exactly how it works with the reentrant lock. When it's non-fair, it just uses an unordered set of things. And if it's fair, it uses an ordered sequence. Obviously, that's more expensive to maintain the order than just to keep elements unordered. But this is the way how it's done. Okay, so now—
I'm sorry, Marcus, can I check something here? Sets are all unique, but they're not necessarily ordered. Sequences
are ordered, right? You lost audio. You lost audio, Honorio. But yeah, sets, no order, no duplicates, sequences, order, thus duplicates. Okay. Anybody else here that can still hear me?
Yep, I can still hear you. He did lose audio. I stopped hearing him by the time you said it.
Okay, great. Okay, so I guess this kind of concludes the part about TLA Plus. So there's time for questions.
I have just a quick one. So are you just running that in VS Code and with terminal commands, or is there like a standard set of scripts that you would use or tools?
So there is a full-blown IDE based on Eclipse that I think is perhaps in 2022 not sexy anymore, but which provides the best first user experience. It has the most guidance. I would suggest starting with this one. With the VS Code extension, it's more bare bone, it's more lightweight, has fewer features, less guidance. So download the TLA Plus toolbox. That also comes with a bunch of examples, beginner examples, and Lamport's video course, from which I stole the screenshot with the clown nose. That also introduces the TLA Plus toolbox and is built on the TLA Plus toolbox.
Excellent. That answers my question. Thank you.
Other questions?
Hi.
Hi.
I have a question. As far as I know, PLC model checker itself has deadlock checking, right? So I'm just curious why we used environment instead of deadlock checking.
Oh, right. So let me just rephrase the question. So here I stated this invariant, right? Where was it? I think earlier it was called no deadlock. Whoop. This was called no deadlock. Now it's called invariant. And TLC happens to have a flag. Check it here. If I remove this deadlock checking, then we wouldn't have to state this, or there's no deadlock anymore, so it doesn't find a deadlock. But there's built-in support in TLC for deadlock specifically. The reason why I didn't use it is it looks more magical, and it also only works for deadlocks and doesn't work for arbitrary safety violations. Whereas this is really the technique to state arbitrary safety violations. I hope that answers the question.
I see. Thank you. Thank you. I got it.
More questions?
Hey, Marcus, Dan here. Just
Yeah.
I guess, shout out quick. Thanks. This is awesome intro. I think you gave us kind of a good how and what, but I guess I'm curious a little bit of like, from your experiences, when do you tend to use TLA? Like to me, it feels like it's somewhere in the middle, right? It's not like test first, testing where you're doing it ahead. It's not necessarily when the problems are there. I guess just kind of thinking through that. What's your thoughts on?
Yeah, that's a great question. So the short answer is that I've never written a spec that afterwards I thought, okay, this was a waste of time. This has never happened to me. Whenever I've written a spec, it kind of paid off. There were multiple occasions where I didn't write a spec because I thought, okay, this is easy. And then in hindsight, I thought, dang, I should have written a specification. But that's just my personal observation. I think more generally, there is obviously, I wouldn't say overhead, but there's a cost of writing specifications that usually you get some return on later because you don't run into issues. To give you an example, I once wrote for the TLC model checker itself, I wrote a weight-free hash set that has some parts of it in memory, the other parts on disk. And again, this is all weight-free, so there is no locking whatsoever. This is notoriously difficult to get right. So I wrote the specification. I was interested in performance, so I also wrote a couple of prototypes. So I used kind of an iterative process. And once I was done, was happy with the performance, was happy with the correctness, because the model checker gave the green light. I wrote the final implementation. And once I shipped it, I've never gone back and changed a thing in this piece of code. There was no bug, right? And that was just me, a single person, writing the specification and the implementation for something that's, yeah, notoriously difficult to get right. Another example is if you think of any other engineering discipline. I know it's kind of old to talk about building skyscrapers, but when you build a skyscraper, you don't start out with laying out the foundation and then somebody else starts building the interior. No, everybody starts building more models and models and models on top of models before everybody is kind of happy that this is good enough, and then the real work starts. And I think software engineering is not there yet, which is, I think, and TLA Plus is one way to fill this gap. If you look at the, now more hands-on, look at the, where is it here? The set of examples. We have this examples repository on GitHub. There are 85 examples. You will find quite a few for textbook algorithms. For example, or more specifically, Raft and Paxos, two consensus algorithms, which both have been kind of designed with TLA Plus. Other textbook algorithms, bakery algorithm, and so on. But for example, also here, the specification of how this thing called level checking works in TLC, or of the TLC model checker itself. Or more technically, I can point you to, where is it? To this beautiful blog post here, using TLA Plus in the real world to understand the glibc bug. That's related to this broadcast and signal that I talked about earlier. And here, the author uses it to really reproduce a real world issue in this library. There are a few more for Python code, issues in Python code, and then also other distributed systems like the implementation of Raft in MongoDB, and so on and so on. There's a fair number of specifications that are perhaps a little bit more, I would say, enterprisey, where you have the integration between Kubernetes and something that runs on top of Kubernetes, something like that. Those tend to be kept private, written by some companies such as Microsoft, right? And they don't share it, which is a little bit unfortunate. But yeah, usually it pays off to write the specification. Oh, it was a long-winded answer.
No, that was good. You showed us some things that you hadn't referenced before, so good to get into it. No, I think that answered it. I think you did sum it up at the beginning. Like, there's a cost, and right, it's all about that value equation we have to think about as we build things. So awesome, thank you.
I was going to say, I think Steve McConnell in Code Complete made the same analogy about, if I was going to build a doghouse, I'm not going to sit there and draw blueprints. But if, like you were saying, if I'm building a skyscraper, then I'm going to do models, I'm going to do site surveys, I'm going to do a lot to make sure it works right. So yeah.
Right. I mean, if it's something,
there is a question in the chat too, Marcus.
I don't see this. Let's see. Seems like many actions in TLA Plus are atomic and signaling instantaneous. 10-1 model processes which interact over a specified duration or range of times and perhaps find ways in related conditions. That's a good question. So in TLA Plus, an action by itself is atomic. But if you want to, for example, model something like message passing, you would have a variable that represents the channel, and then you add an element to the channel in one action, and you would have another action that removes the element from the channel again. And that way you get this non-atomic interactions and also get the model checker to check all possible interleavings. So that's very well supported. I don't know if you're also interested in real time. Sound a little bit like that. Lamport wrote this paper with a catchy title. No, I have to make sure I get this right. Real time is real easy or something like that. Essentially, he shows in the paper how you use TLA Plus to check real-time systems with time advancing. But yeah, okay, yes, real time. So yeah, this paper, real time, let's see, Lamport, real time, real easy, I believe. Real-time model checking is really simple and real-time is really simple. Those are the two papers that I would recommend when you're interested in checking real-time. Because if you think about it, checking real-time properties is actually just checking safety properties, because there's a finite sequence of states before you run into a state that violates the real-time guarantees. Yeah. Other questions? More in the chat or check out the papers. Okay. Well, if there are no more questions, then let me just, yeah, go ahead.
All right, I'll ask it since no one else seems to be wanting to ask it. If somebody wanted to get started with TLA Plus, where would you suggest they start? Okay.
Again, good question. Where are my slides here? Okay, so the best freely available course is Lamport's video course that he recorded a couple of years ago. That consists of 10 episodes or so, or 11 episodes, aka.ms/TLA, where he really gets started at the beginning. What is TLA Plus about? Every episode is perhaps half an hour, 20 minutes to half an hour. But don't be discouraged if it takes you 3 hours to watch one episode. It's dense material. You can also go to GitHub, find my material here at akm.ms/TLABQ, TLA blocking queue. They can retrace today's tutorial here, and there is more in there. There's stuff about the proof that I haven't really shown you. You can probably just skip over it. There's stuff about how to relate the implementation, how to check that the implementation conforms to the implementation. And there's also stuff in there, which is actually my homework assignment for you guys. And if you want a homework assignment, let's see, where's the history? Code. Oh, I think I have to click here. So this was kind of working backwards, right? We had a specification. We had an implementation from which we derived the specification and then found 2 bugs: starvation, liveness issue, and a deadlock, a safety issue. Now let's say, while we're at it, right? Now we finally touched this code base, so let's now add this feature that has been missing forever, which is graceful termination. So how do you gracefully terminate this system where you have an arbitrary number of producers, arbitrary number of consumers, and you want to stop all of them with an empty buffer? So you don't want to kill them, you don't want to lose data in the buffer. You want to make sure that this all works. So this is now kind of forward designing a new feature. The solution is in the repository. I don't want you as homework assignment to specify the TLA Plus, but try and sit down and on a piece of paper or Word document, try and specify the algorithm in prose, right? It doesn't have to be formal math. It doesn't have to be TLA plus, that you think would make sure that this requirement works. Because this is probably the best way to learn TLA plus, to get used to this formal thinking. And then once you're done with your solution, compare it to mine. And it's surprising because there are many answers to this question on the internet. And there are quite a few that are actually incorrect, even on Stack Overflow and paid sites where you would expect some level of quality. Other questions? Oh yeah, I know. Also, we'll be back in a second. There are 2 books that you can buy, which this one you get for free even, as the online electronic version, Specifying Systems by Leslie Lamport himself. That's kind of the canonical book on TLA plus with advanced features. This one is more hands-on, practical TLA plus. It's mostly the Pascal dialect that sits on top of TLA plus, which has extra syntactic sugar that makes TLA plus look more like an imperative programming language. And it comes with lots of exercises. So this one is also nice.
If anyone else has any questions, feel free. I guess no one else has any questions right now, or they're too shy to say something. Okay, well, then I will say thank you so much for your time, Marcus. Really appreciate it.
Yep, it was fun.
Yeah, thanks, Marcus. Really appreciate you coming out. This was super interesting. And I've got plenty of concurrent systems that I'm interested in testing this out on.
Yeah, great. Okay, thanks for having me.
Okay.
Excellent.